Good morning, everyone. I'm Ms. S. Selvanyaki, an assistant professor in the Department of Computer Science at Sri GVG Visalakshi College for Women. Today, I'm excited to present to you on the topic of MC-CLUSKEY. In this session, we will explore the fundamentals of this important method, its applications, and how it can be used in digital logic design. So let's get started and dive into the fascinating world of MC-CLUSKEY. Let's talk about why Boolean simplification is so important in digital design. Essentially, simplifying Boolean expressions helps us create more efficient circuits, which means faster operation and less hardware. One of the key methods used for this purpose is the MC-CLUSKEY method, also known as the tabular method. It's a systematic approach that allows us to methodically reduce complex Boolean functions. This method is particularly useful when dealing with functions that have many variables, where manual simplification can become very complicated. Overall, mastering this method is crucial for designing optimized digital systems, and it ties directly into the larger theme of creating efficient, reliable digital circuits. Let's talk about the determination of prime implicants. Prime implicants, or pies, are essentially the terms that can't be combined any further. Think of them as the most simplified building blocks in the process. Each prime implicant represents a group of minterms, which are the specific combinations of variables that satisfy the function. These pies are really important because they form the core of the simplified Boolean expression. By identifying these prime implicants, we ensure that the simplified function is as efficient and as minimal as possible, which is the ultimate goal of the simplification process. So, understanding how to determine these prime implicants is key to mastering Boolean algebra simplification techniques. Let's look at an example problem to see how we simplify Boolean expressions. Here we have the function f of four variables, a, b, c, and d. The function is given as a sum of minterms, which are indicated by these numbers in parentheses. These numbers represent the specific combinations of a, b, c, and d where the function outputs a 1. So, for example, minterm 0 corresponds to a equals 0, b equals 0, c equals 0, d equals 0, and minterm 1 is a equals 0, b equals 0, c equals 0, d equals 1, and so on. Our goal is to simplify this expression, making it easier to implement in a circuit. By identifying common patterns among these minterms, we can reduce the overall complexity of the function. This process is essential because it helps us design more efficient digital systems. So, as we go through this example, keep in mind how we're transforming a potentially complicated expression into a simpler form. All right, let's talk about how to determine prime implicants. First, the key step is to combine terms into reduced forms, and you'll notice these forms often include a dash, like a hyphen, to show the combined bits. This step helps us simplify the expressions by merging terms that differ in only one position. Next, the terms that can't be combined any further, these remaining terms, are exactly what we call prime implicants. They represent the essential parts of our minimized expression because they cover the parts of the function that can't be simplified further. And finally, once we've identified these, we list all the prime implicants for the function. This list is crucial because it forms the foundation for constructing the minimal sum of products or product of sums. Remember, understanding how to identify prime implicants is fundamental in simplifying logic functions efficiently. This slide doesn't contain enough information. That's why we're moving to the next slide. Now, let's talk about the selection of prime implicants. The first key point is about essential prime implicants. These are the ones that cover minterms which no other prime implicants cover. Essentially, they are critical for ensuring that all minterms are covered without redundancy. So, the first step is to identify and select all the essential prime implicants. Once we've done that, we need to look at the remaining minterms that might still be uncovered. If any minterms are left, we add non-essential prime implicants that can cover these remaining minterms. This process helps us to create the most simplified and efficient logic expression possible. Remember, selecting the right prime implicants is crucial for optimizing our circuit design, so paying attention to which are essential and which are not is a vital step in the overall process. This slide doesn't contain enough information. That's why we're moving to the next slide. So, in conclusion, the McCluskey method is a systematic way to minimize Boolean expressions. It helps us break down complex logic into simpler, more efficient forms. Prime implicants are really the key step here because they form the foundation of our final expression. They ensure we don't miss any essential parts of the logic while simplifying. When we look at the simplified result, it's expressed as f of a, b, c, d equals plus cd plus ac. This shows how we combine the prime implicants into a minimal, efficient form. Overall, this method provides a clear, structured approach to simplifying logic functions, which is crucial for designing optimized digital circuits. Thank you so much for your time and attention today. I really appreciate you being here. I hope you found the insights and information valuable and that it helps you in your own work. Remember, the key points we discussed, whether it's the strategies, the data, or the takeaways, are all about empowering you to make better decisions and drive positive change. So, thank you once again for your engagement and interest. I look forward to seeing how you apply these ideas moving forward. Have a great day.